Hi everyone, my name is Ito Ding. I'm at Chemnitz University of Technology in Germany. Today I will talk about how we improve safety and accuracy of impedance-controlled robot manipulators with proximity perception and proactive impact reactions. If robots and humans work in the same workspace, then safety is of highest interest. And we can consider actually the safety as layers, where in the highest layer we have the workspace monitoring, where we can do planning and create motions or pre-plan the motions of the robot according to the current situation. And if we have dynamic obstacles, for example, humans that are running around, we can use collision avoidance to react to dynamic obstacles. Then we can create reactive motions with that. But in the most inner layer, we have impact attenuation, which means if all the above layers fail, we can use impact attenuation to reduce damage to the robot or to the human as last safety layer. So this work actually focuses on this last layer. So proximity manipulators attached to the robot's outer shell have shown robust collision avoidance capabilities in the past. But what if collision avoidance fails? For example, the motions that must be used for the collision avoidance could be out of the robot's capabilities. For example, a human could be approaching the robot too fast, and the robot can't move quickly enough to avoid the collision. And common solutions actually to attenuate impact rely on soft padding, for example, or rounded shapes, and also flexible joints. But also another solution are vector joints, where we can use them in combination with impedance controller to render a virtual spring damper system. So actually the joints are then rendered as virtual spring, and which means when we apply external forces, the robot would deviate from its original path. However, this solution has a problem. Before we get the external forces, we have to first compensate its own forces, the robot dynamics. And this means if we have errors in our model, inaccuracies in our model, or even torques, sensing errors of the torques, we get errors in our external force estimation. And this means if we have, for example, very low spring stiffness, the robot will deviate from its path even more. And that's a common problem if you want to achieve accuracy. So the control paradigm actually for impedance controlled robot is actually stiff and slow, and fast and soft if you want to achieve the same safety. And this means we trade off accuracy for speed to remain safety. The objectives of this work are as follows. We want to proactively react to impacts. And that means we can use the proximity information to react just as required. For example, if in regular operation where the robot just does its normal motion without obstacles, the stiffness can be very high and achieve very high accuracy, even though with high velocity. And as soon as an obstacle approaches, we can use the information, we can detect it with proximity sensing, we can reduce the stiffness just as required, and then the robot will lose some of its accuracy, but it will be very soft and remain safe. Furthermore, we have another method which we are using, which is the reconfiguration of the robot joints, which means if we anticipate an impact, we align the joints towards the impact so that even more joints can participate to the attenuation. So before we start with our methods, I want to give a short intro to the system we are using for proximity sensing. So proximity perception is actually not new. It's a concept introduced in 1989, and it's an inside-out view concept compared to external camera systems. The inside-out view allows us to have no occlusions, and actually anything that occludes the sensor is an obstacle, which is of interest for us and creates to very low amount of data. And this allows us to have very low latency for very fast reactions. And another point is, since proximity always precedes touch, we can react actually earlier before collisions actually occur. In this work, we are using 3 proximity sensing cuffs attached to our robot, and each cuff has 8 to 12 sensing elements. So the sensing cuff at the end effector uses 8 elements, and each of the elements has time of flight sensing, laser time of flight sensing up to 1 meter. And we also additionally use capacitive sensing for the very close proximity area to cover large areas, and also to cover the areas where the laser time of flight sensors are blind. Okay, so let's start with the first method, relying on the modification of the stiffness parameters to attenuate impacts. And actually the idea is very simple, which does not actually require much explanation, but just think about it. If an obstacle comes close, detected by the proximity sensor, we want to reduce stiffness, and if it goes away, we want to increase it again to have high accuracy. However, if you think about it again, if we have a compressed spring, you can't increase the stiffness as you like. If you increase it suddenly, you have a system where the energy in the system increases, and where a system where the energy increases can be unstable, and that means we have to take care of that. And in order to do that, we have a stiffness rate control, as you can see here. So the stiffness is changed according to this graph and is the input into the stiffness rate control, and the stiffness rate control limits the rate of stiffness changes. And also in the output of our stiffness rate control, we have an energy observer based on energy tanks. If the energy in the system increases too much or too fast, the stiffness control will actually reduce the rate of control, a rate of change to avoid instabilities. Okay, let's discuss the second idea, which relies on the reconfiguration of robot joints. The idea is that aligning the robot joints towards the impact direction will increase or render low inertia, since more joints can participate in the impact attenuation. If a joint is actually 90 degrees not aligned, it will not take place in the attenuation part and will increase the inertia. And the way we're doing it is we calculate the manipulability at the impact point, which is in the direction towards the impact direction. And that manipulability, for that manipulability, we're calculating the Jacobian. The first Jacobian is actually the normal Jacobian starting from the base of the robot towards the point on the collision. And in order to incorporate the rest of the robot to decrease the inertia, we also flip the robot around. We calculate the Jacobian starting from the TCP towards the collision point. And with that Jacobian, we can use it to increase the manipulability with our previous released collision avoidance framework based on quadratic optimization. And we can use that or add that to our optimization term, and it will automatically optimize the joints towards to increase the manipulability. Let's see some tests where we throw some objects towards the robot. In our first test, we keep the standard impedance controller, and as you can see, the robot does not absorb much energy. In the second test, we implemented our 2 methods, and the robot joints before the impact will align a little bit towards the impact direction to attenuate impact, and also the stiffness changes to lower stiffness before the impact occurs. And after the impact, the robot goes back towards the original position, and that means that the stiffness is actually increased again to the original high stiffness parameter. And you can also see that the robot maintains stable, which means the energy tank observer does work. Here you can see 2 plots. In blue you can see the manipulability of the impact point towards the impact direction, and in red you can see the distance to the obstacle. On the left side you have the reconfiguration of the robot turned off, and on the right side it is turned on. And as you can see, on the left side the manipulability is actually lower compared to the right side, which means the reconfiguration works as planned and increases the manipulability towards the impact direction. And here you can see two plots. On the left side in blue you can see the distance towards the obstacle, and in red are the joint errors. The joint errors will increase when the obstacle comes close because the stiffness decreases, and the joint errors will reduce as soon as the obstacle goes away. On the right side you can see that in blue the joint stiffnesses, and in red is the energy within the energy tank. And what you can see here is that the energy tank depletes when the joint stiffness increases, and that means when it is depleted, the energy tank, it will limit the rate of increase of the joint stiffness to remain stability of the system. To conclude everything, we have presented a fast-reacting impact attenuation method relying on the modification of impedance parameters and reconfiguration of robot joints. And our method should be applied in conjunction with collision avoidance as a last safety net. And we also overcame the accuracy and speed limitation problem of pure impedance controls. Thanks for your attention, and see you next time.